Scientific measurements. Scientists are very careful when they record measurements. What is this? Carbon monoxide concentration in the air, different years. So same data, basically, but here it's listed as 8.9 parts per million, 6.2. Over here it's 9 and 6. When scientific measurements are reported, we record all the digits that we're certain of and one that we're guessing at, an estimated or uncertain digit. So when we look at this number, 8.9, the last digit is estimated. And so generally speaking, you can assume that it's plus or minus 1 in that last digit. So that would be 0.1. So that's plus or minus 0.1. Meaning the scientist is saying this is between 8.8 to 9.0. That's my range. I'm saying it's in there, it's 8.9, but the 9 is a little iffy. Over here, there's only one digit. That one digit is the last digit, meaning it's uncertain. So there's plus or minus 1 in that digit. That's the ones place. So this is 9 plus or minus 1. That means it's between 8 and 10. That's a bigger range. We don't know that number as precisely as we do this other one. And so scientists are very careful when they record their measurements. We don't just round stuff off to have nice round numbers. We record things very carefully to imply how closely we measured them. Last digit, always estimated. So we're talking about analog devices here. There are also digital devices. We've got digital balances. The balances just show you digital numbers. Easy peasy. You just write down all the digits they give you, and whatever the last one is, that one's uncertain. And sometimes you can see that it's uncertain because it'll change a little bit. You're like, wow, that's really uncertain. Even the balance can't make up its mind. But analog devices, we need to read between the lines. And I'm going to hammer you about this in lab. This is important. Read between the lines. What does that mean? Well, that means that we're going to estimate between the lines on the measuring device. You look at the device and say, what does the smallest line represent? So here, this is 0, and this guy down here is 10. So each of these little lines represents what? 1 gram. So 1 gram is where the lines are. We look, this is a pistachio, right? We look and we see that it is very clearly between 1 and 2. There's no uncertainty in the 1. It's between 1 and 2. It's 1 point something. But there's no lines in between. So we're going to estimate. And you kind of just mentally divide that into 10 spaces. You say, well, it's not halfway. That would be 0.5. But it looks like it's, just a little closer to the 1, and so you may estimate it as 1.2. So a good reading for that would be 1.2. Now somebody else might record it as 1.3. That's okay. There's uncertainty in the last digit. So we're always going to estimate 1 decimal place past the smallest division. So if you have a ruler that has 0.1 centimeter divisions, you're going to record your measurements with 2 decimal places because you're going to estimate between the lines. You're going to read between the lines. If the thermometer has markings that are 1 degree Celsius, the markings are on the ones place, you estimate to the tenths. Any questions? So you'll look at the instrument. We're going to use burettes and graduated cylinders and beakers and all kinds of different things, and rulers. Whatever the smallest line represents, go the next decimal place and you estimate. What do you do if it looks like it's right on the line? You still need to put the place there. You put a 0. because it looks like it's right on there, and so you put a 0. So the precision of a measurement depends on the instrument. If you use a ruler that only has meter divisions on it, or if you use one that's got millimeter divisions, you're going to come up with different sorts of accuracy or precision in that data, right? Because we're reading between the lines. So we measured all these things carefully, and then we need to be careful what happens when we do calculations. And this is where significant figures come in. Because if we think about maybe a crazy example. So let's say we measured something and it was 12 no, 12's not a good number. 11. Piece of wood, 11 meters long. What's the uncertainty in that? In the ones place, right? And so we're saying, oh, it's between 10 and 12 meters. It's kind of a rough measurement, isn't it? We're like, yeah, it's about 11 meters long. What if we took that piece of wood and divided it into 3 pieces? What would the length of each piece be? Well, the calculator is going to show you this, or something like that. Does that mean that each of those 3 pieces is 3.66666667 meters long, and that the uncertainty is way over here? No, that's silly, isn't it? But that's what happens with the calculator. And so significant figures allow us to do calculations and then round the answer in an appropriate way to preserve the meaning of that number, to preserve the impression of the precision. So significant figures rules would tell us that we should report that as 3.7 meters, and that's what we might end up with. So that's what significant figures do. Students often don't like significant figures. It's a little bit like learning to play a game. Like, why would I want to play a game that isn't any fun? To pass the class? I don't know. But we can do significant figures, or we can do differential calculus. Who votes for differential calculus? Yeah, I didn't think so. I don't want to do that either, because I did that in college, and then I promptly forgot it. I remember that I did it. I could figure it out again, but I couldn't do it off the top of my head right now. So we're going to do significant figures instead of differential calculus, if that gives you a better feeling about it. So when we talk about a significant figure, I sometimes call them sig figs, because significant figure is really long to write, and there's too many syllables to say. They're also sometimes called significant digits. Those include all the certain digits in the number and the first uncertain. So when we record a measurement, like, we were talking about like 1.2 grams was the example of that other one. We include the certain digit and the first uncertain. And so sometimes there's only one digit, and that would be the uncertain digit. But that's what we mean by significant figures. The more significant figures there are, the greater the certainty of the measurement. And so to figure out how many significant figures are in a number, there's some rules, and we have some examples. It's really just the zeros that give us trouble. All non-zero digits are significant. These are examples. In bold are the non-zero digits, just in case you weren't sure what wasn't a zero. Non-zero is everything but the zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Always significant. It's just the zeros. So there's 3 kinds of zeros. There are interior zeros. These are ones that are trapped between. Like this guy's trapped. He's interior. He's on the inside. That one and this one. Those are always significant. Leading zeros are not significant, ever. So leading zeros come at the beginning of the number. We read left to right, and so as you read left to right, zeros that come at the beginning are leading. They lead the other numbers. So those guys, they are important, but they're just holding the decimal place. If we took them away, it would become 0.23, a different number. We need them there, but they don't reflect a measurement. And over here, we've got 2 leading zeros. Those are not considered significant. So we would say this number has 4 significant figures, and this one has 2 significant figures. And then trailing zeros. I think of trailing zeros a little differently than the textbook does. You'll come up with the same result. So if you like my way, awesome. If you like the book's way, fine. But it's my class, so I'm going to teach my way, right? So trailing zeros. So what we're concerned with here is there a written decimal point? If there's a written decimal point, actually written out, here's a trailing zero, 39.0. Trailing zeros come at the end. Leading zeros at the beginning, the trailing zeros trail after. If there's a decimal point, it is significant. Because would we write that 0 to hold a decimal place? If we wrote 39 instead of 39.0, does it really change the value of the number? No. Let's try that. So if we got rid of the 0, 39 or 39.0, those are essentially the same thing, right? This one above, if we got rid of all those zeros, we'd have 0.23. Is that even close to the same? No. Those zeros are holding a decimal place. In this example, we can see that that 0 is not really serving a function. Why did we write it there? We wrote it there because that was our estimated digit. This measuring device had markings of 1, whatever it is. And so we estimated the next place. And we said it looks like it's right on the line. So it's 39.0. If it looks right on the line, does that mean it's exactly 39 centimeters? No, there's uncertainty in every measurement. But as far as we can tell, it's 39.0. Here we've got 1.432000. There are trailing zeros. There is a written decimal point. Those are significant. Here we have 120.00. Now this 0 is before the decimal point, but that doesn't matter. These are all trailing zeros. They're significant. 29.310, trailing 0, there's a decimal point. If you have trailing zeros with an implied decimal point, so here, 300. If we were going to put a decimal point, where would we put it? We'd put it right here, wouldn't we? We know where it goes. Is it actually written in there? Nope. These are trailing zeros. There's no decimal point actually written. We don't know. Are those uncertain digit? Is that last one an uncertain digit and the one before it is a certain digit? Or are those needed to hold the decimal place? So we say they're ambiguous. We don't like ambiguity in science. We want to know this way or that way. So we want to avoid these trailing zeros. Here's another example. Zeros at the end, no decimal point. Zeros at the end, no decimal point. So they're ambiguous. Should we say, what if we were forced? Mastering chemistry is making me put in a number. I can't type in ambiguous. It won't take it. What do I do? Then we want to assume the worst case scenario, because it would be better to overestimate the amount of error and say, well, that's about 300, rather than underestimating the error and saying, no, that's 300 decimal point, that's to the nearest one. So we would say that these are not significant if we were forced. If we had to identify the number of significant figures, we'd say this one has 1, and this one has 4, and that one has 1. Now, a number like 100,000, well, let's think about the population of Fresno. Anybody know what the population of Fresno is? Pardon me? Okay, 600,000. So what do you think the error is on that? Maybe plus or minus 100,000? Could it be 500,000? Yeah. I think it's actually a little under 500,000. We're not talking Clovis, we're just talking Fresno. Because the Clovis, that's another place, right? They're right next to each other. So 600,000, that's an estimate, isn't it? And so we see a number like that, and if you're saying, okay, there's 600,000 people in Fresno, we don't want someone to think that we actually counted all the people and there's exactly 600,000 to the nearest one person. Well, what if it was to the nearest 1,000 that we estimated? We had some, actual data instead of just guessing off the top of our heads. How would we indicate that there was uncertainty in the thousands place? We could put a plus or minus. We could say plus or minus 1,000. We could do that. The other thing we could do is we can put this number in scientific notation. Because in scientific notation, all the insignificant zeros go away. The leading zeros and these ambiguous trailing zeros. So, quick lesson in scientific notation. To put this, there's an implied decimal point over here. We need to move that over here. Sorry, come on. No, I don't want to do that. Just arguing with the iPad. So, we move it 1, 2, 3, 4, 5 places. So that's going to be 6 times 10 to the 5th, because the exponent is the number of places you move the decimal point. Then you have to decide, is it positive or negative? 600,000. Is that a big number? Yeah? Think $600,000. I have positive feelings about big salaries, big paychecks, positive feelings. Big number, positive exponent. Small number, if that was 0.001, that's a small number, right? Then the exponent would be negative. Little paycheck, negative feelings. So if this is to the nearest 1,000, we're saying the uncertainty is right here. So then we want to keep those 2 zeros. Because in scientific notation, we only write significant figures. We never, ever need these to hold a decimal place. If we take this number up here and put it in scientific notation, so 0.00, sorry, it's getting smaller and smaller, 23. I keep zooming out in different levels. We're going to move the decimal point to after the first non-zero digit. I should do that in blue. We're going to put it over here. 1, 2, 3, 4. So it's going to be 2.3 times 10 to the 4. We have to decide plus or minus. Small number, small paycheck, negative feelings, negative 4. These zeros went away because we don't need them anymore. And we're not going to add any zeros on at the end because there weren't any here to start with. So we can avoid those ambiguous trailing zeros by using scientific notation. Questions? Exact numbers. There are some numbers that are exact. One example is exact counting of discrete objects. How many fingers am I holding up? Are you sure? 4. 1, 2, 3, 4. We can count them, right? There's not 3.5. There's 4. I purposely didn't do 5 because somebody would argue that my thumb is not a finger, it's a thumb. So I don't want to go there. 4. We can count that. So things that you can count discretely, it's an exact number. So if you, well, how many significant figures does it have then? An infinite number, right? 4 fingers, 4.000, you could say 0 forever. It's exact. You can count things and have an exact number. Now, if you're counting much larger numbers of things, like if you were to count the number of people in Fresno, just you yourself by yourself, it would take you a while, right? And between you counting the first person and counting the last person, some people would have died and some people would have been born, and the number was changing, right? So when you get to counting really large numbers of things, it kind of breaks down, but use some common sense on that. Integral numbers. An integral number means an integer, a whole number, 1, 2, 7, 59, things like that. Integral numbers that are part of an equation. Those are said to have an infinite number of significant figures. So the volume of a sphere is 4/3 pi r cubed. The 4 and the 3 are integers. Also, defined quantities. 1 inch is exactly equal to 2.54 centimeters. Remember in the that table of conversion factors, I pointed out that this one was exact. So if you're using these numbers in a calculation, then we say it has an infinite number of significant figures, so we don't have to worry about them. Some conversion factors are defined, some are not. If you're going between systems, and this is between systems, this is between the English system of inches and the metric system of centimeters, usually those are not exact. But a foot and 12 inches, 1 foot is exactly 12 inches by definition. If you're within one system or within the other system, usually those are exact. Examples. How many significant figures in each of these guys? 0.0030 liters. 2. How about the next one? 4. How about number 3? 4. There's an interior 0 on that one. How about number 4? 3. We could also say that's ambiguous, but if we have to put a number. 29 pencils. Unlimited. 5,069 milliliters. 5. And that last one. 4. Good. So trailing 0, there's a decimal point here. And so that trailing 0 is significant. These guys are all leading zeros. It doesn't matter that some of them are after the decimal point. Any questions? Like I mentioned earlier, when we do a calculation, we shouldn't gain or lose precision just because of the math that we're doing. And so we need some rules to help us know how to round off the result. In multiplication or division, those are like opposites of each other, right? The result is going to have the same number of significant figures as the factor with the fewest. So this example is all written out. We've got 1.052 times this times that, and the calculator gives us an answer like this. And then we write that down, and then we go back and figure out what should we round it to. So we look at how many sig figs in this number. Well, this number has 4. How many in this one? This one has 5. How many in this one? This one has 2. Then you look at those numbers. Which is smaller? 2, 5, or 4? Duh, it's the 2, right? This one has the fewest number of significant figures, so then our answer has to be rounded to 2 significant figures. So we're keeping the 6 and the 7. We're going to get rid of the 2. That's smaller than 5, so we'll just drop it off, and we'll report this as 6.7. Another example, these two guys, this one's got 5 sig figs, 3 sig figs, 3 wins, so when we do this, we end up with 3. You need to be careful if the last place you're keeping is tens or hundreds or thousands, that when you round your number, you don't change its magnitude. I think I have an example on that, but maybe I don't. No, I don't. Let's just do something really quick. What if we had 4,972 meters, and we needed to round that to 2 significant figures? would that be 50 meters? No, that's silly, right? Because it was 4,972. That's almost 5,000. We can't just make that 50. If you want to do that, I'll do some business transactions with you and I'll make a pile of money off you. We can't do that. We're keeping 2 sig figs. Why? Because I said we were going to. So we're going to keep the 4 and the 9. This is the hundreds place, right? It's above 1. We've got to be careful. Best thing to do is to put it in scientific notation and then round it off. Because people lose their minds, especially on an exam. You're good until you write your name on the paper and look at the first question that just like vacuum between your ears. If we put this in scientific notation, 4.972 times 10 to the third. Now if we round it, we're dropping this 7. The 7 is 5 or greater, so we'll round the 9 up to 10, which rounds the 4 up to 5, and we're going to get 5.0 times 10 to the third meters. So just watch out for that, because people do some wacky things when they round off big numbers. Addition and subtraction. The result carries the same number of decimal places as the quantity with the fewest decimal places. And the best way to think about this is actually to stack the addition. There's no add sign on that one. Stack it up like you were going to do it by hand. And look what happens. So on 2.345, what's the uncertain digit? The 5. It's always the last one, right? 0.07, where's the uncertainty? The 7, and 2.9975. 5. So when we're adding these, we're adding the 5 to, we have no clue what that number is. We have to assume it's 0, but we don't know anything. And this one's really uncertain as well, and that 5 is uncertain. So when we do the math and add that up, that 5 is uncertain, right? And then over here we've got a 5 that has uncertainty, plus who knows what, plus a 7 that we're certain about. So that adds up to 12, but we're not certain about the 2 because of the uncertainty in the 5. And then we go over here, a certain 4, uncertain 7, certain 9. This isn't certain either. When we add this guy, 3 plus 0 plus 9, now we're getting some certainty. And so the rest of these are going to be certain. But when we record a number, or when we record the result of a calculation, we only include one uncertain digit. And so that's why we're going to keep the 1, and we're going to drop the 2 and the 5. And so we'll report the answer here. The other way to think about it is, here, this one has 1 decimal place. This has 3 decimal places. So 1 decimal place is how many decimal places I want in the answer. So the 7 would round this up to 5.7. So we go with if the digit you're dropping is 4 or less, you round down. 5 or more, you round up. We're not going to do the odd even thing with the next one. So if we look at this one, 3.49. Sometimes people want to do crazy things and they want to start at the far end and round all the way backwards. No, that makes it way too hard. Because then, and you sometimes get the answer wrong too. You would round, 9 would round the 4 up to a 5, and then the 5 would round the 3 up to a 4, but that's not what you do. We're rounding all of these to 2 significant figures. We're going to keep the 5 and the 3. You just look at the first one that you're getting rid of. It's less than 5, round down. Ignore everything to the right. We don't want to have rounding errors. So when we do a multi-step calculation, do the whole thing through on your calculator and write everything down, and then go back and look at what's going on in the actual calculation. It gets tricky when you've got multiplication and subtraction mixed together. You have to look at the result of this. The result of that is 0.479. 2 decimal places, 2 decimal places. And so this actually has uncertainty in the second, I'm sorry, that has 3 decimal places, this is 2. This has uncertainty in the second decimal place. So one thing we sometimes do is I'll underline that just to let myself know that one's uncertain. And then I'm going to do all this multiplying. This one, though, only has 2 sig figs, 4 and 3. And so then I round my final answer to 2. So you can go home and do some examples. I'm done. I'm done. I'm sure you're past done.